In this video, I'm going to be going over 4 free body diagram practice problems. So we'll start with question number 1 here. The reason why I'm starting with this question is because if you look at the picture, it is a game of tug of war, which was the analogy that I used in my free body diagram explanation video. If you want to watch that video, you can click on link number 1 in the description. If you want to skip to the part where I talk about the tug of war analogy, you can click on link number 2 in the description. So question 1 asks, how many pounds of force, which is LBF, stands for pounds of force, how many pounds of force does person X have to pull to win the game of tug of war? So we see a picture of 2 people pulling on the left, 2 people pulling on the right, one of those being person X. It seems pretty obvious what the answer is going to be, but the first thing we'll do is we will start by drawing the free body diagram. So we'll just draw a simple box like this, and then the forces are represented by the directions and the magnitudes, the directions being what directions the forces are going, and the magnitude being how many pounds of force, in this case, the forces are. So I'll start by drawing the free body diagram. You can see pulling to the left, you have somebody pulling 90 pounds of force. So I'll draw the arrow with 90 pounds of force. And then on the left side, you also have somebody pulling 110 pounds of force. On the right side, in the opposite direction, you have 80 pounds of force by this person. And then in the same direction as the 80-pound person, you have person X, which is who we're trying to solve for. So since this tug of war game is taking place in the x-axis, we are now going to find the summation of the forces in the x direction. So I'm going to set it up, summation of the forces in the x direction. So we have negative 110 pounds minus 90 pounds because they're acting together. And then I'm going to say plus 80 pounds, plus because it's going against the grain, it's in the opposite direction. So plus 80 pounds. And then plus x, and then I'm going to make it equal 0 because we want to solve for x to see how much force he needs to pull in order to win the game. That's why I have it equal 0, so that we can solve for x. Then the summation of the forces in the x direction. When we solve for x, x turns out to be 120 pounds of force. So the summation of the forces in the x direction equals 120 pounds of force in order for the tug of war game to equal 0. So basically, we'll just say that x has to be greater than 120 pounds of force if person X wants to help his teammate win the game. Here's question number 2. Determine the sum of the forces in the x and y directions. This is basically the same premise as the last question, except now we're going to be solving for the x components, which is left to right, and the y components, which is up and down. So the first thing you'll notice is that there's 2 forces here, the 5-pound force and the 12-pound force, that do not act up, down, left, or right. They're acting diagonally. So what we're going to do is we're going to take those diagonal forces and we're going to break them down into their individual components. That is, their individual x and y components, which is up, down, left, right. If you want a more detailed explanation on this, you can click on link number 4 in the description. So we'll start with the 5-pound force, this arrow right here, which is acting 40 degrees from the x-axis. So the 2 components that we're going to be solving for is the y component, which would be the force acting in the up direction, and we're also going to find the x component, which is the force acting to the right. And like I have stated in my free body diagram video, the way you solve for individual components to a main force is the same way that you would solve for legs on a triangle. So to solve for the x component, I would take 5 pounds of force times cosine 40, which is 3.83 pounds of force. So 3.83 pounds of force is acting to the right due to the 5-pound diagonal force. Then the rest of the force is going to be acting up. So to find the y component, it would be just as if I was solving for the y leg on a triangle. Like I stated in my last video, if you have a vector that looks like this, you can actually shift the y components left to right, and you can shift the x components up and down so that they form a triangle. So basically, to solve for the y component, I'm going to treat this like a triangle and just shift the arrow, the vector, to the side so that it forms a triangle. And then I'm going to do 5 pounds of force sine 40, which equals 3.21 pounds of force. So the x component of the 5-pound force is 3.83 pounds of force, and the y component of the 5 pounds of force is 3.21 pounds of force. We didn't get rid of the 5 pounds of force, we just broke it down into its individual x and y components. So now we're going to do the same thing with this 12-pound force here in the other corner. This is another diagonal force that needs to be broken down into its x and y components. So just like similar to how we did with the 5-pound force, we're going to take 12 pounds of force cosine 45, which equals 8.49 pounds of force. That's going to be the y direction. And then the x direction is going to be 12 pounds sine 45, which is 8.49 pounds of force. Basically, we're going to do the same thing that we did with the 5 pounds of force. So to find the x component, I'm going to take 12 pounds sine 45, and to get the y component, I'm going to take 12 cosine 45. They actually equal the same thing because it happens to be 45 degrees, but just remember that the y component, we're taking 12 cosine 45, and for the x component, we're taking 12 sine 45. So 12 sine 45 is going to be 8.49 pounds of force, which is for the x component. For the y component, again, because it's 45 degrees, it comes out the same. But anyway, it's 12 cosine 45, which comes out to be 8.49 pounds also. And now what I'm going to do is just copy the other forces that are not diagonal. Just going to copy them directly from the problem, which is the x-axis and y-axis. So I'm just going to copy them to my free body diagram. So a 4-pound force going up, 6-pound force going down, which is the y direction, then a 2-pound force going to the left, and a 3-pound force going to the left, which is the x direction. So I'm just going to copy them down to my free body diagram. So now that we got the forces, the diagonal forces, the 5 and 12-pound forces into their individual components, what I'm going to do now is I'm going to erase the 5 and 12-pound diagonal forces on the free body diagram. I just want to make it very clear that I did not get rid of those diagonal forces. Those forces are still there. I just erased them because we took those forces and we broke them down into the individual x and y components, which is up, down, left, right. So the forces are still there. We just broke them down into their individual components. And the reason why I do that is so that all the forces are going in the x and y direction. And because we labeled the free body diagram in only x and y directions, it's going to make it easier to do the summation of the forces in the x direction and the summation of the forces in the y direction. So I'll start with the sum of the forces in the x direction, which is positive 3.83 pounds of force, and then minus 2 pounds because it's going in the opposite direction, and then minus 3 pounds of force, and then minus 8.49 pounds of force, which is what we found using trigonometry. So then the answer for the summation of the forces in the x direction comes out to be negative 9.66 pounds of force. And like I stated in my free body diagram explanation video, if a force ends in a negative number, all that really means is that it's going in the opposite direction from whatever numbers you called positive. So basically, negative 9.66 pounds of force just means that it's 9.66 pounds of force in this direction. Now we're going to do the same thing with the y components, which is up and down. So we'll take the summation of the forces in the y direction equals positive 4 pounds of force plus 3.21 pounds of force, which is what we solved for, negative, or, minus 6 pounds of force, minus because it's going in the opposite direction, and then minus 8.49 pounds of force. And then that comes out to be negative 7.28 pounds of force. And again, the negative sign just means that it's going in the opposite direction from the numbers that you called positive. So negative 7.28 pounds of force just means that there's 7.28 pounds of force acting in this direction, which is down. So to answer the question, the net force in the x direction is 9.66 pounds in this direction, and the net force in the y direction is 7.28 pounds of force in this direction, which is down. Here's question number 3. What is the minimum amount of force that person 1 needs to push in order for the box to move to the right? So you see in the picture, there's person 1 who's trying to push the box in the same direction that person 2 is trying to pull the box. So person 1 and person 2 are working together to pull the 90 kilogram wooden box across a concrete floor. So to solve this, the first thing we're going to do is draw a free body diagram. It's going to be a flat surface. It is not on an incline. One person is pushing, the other one is pulling, but they're both going in the same direction, so they're both working together. The only thing that I'm going to do in terms of drawing the free body diagram is I'm going to take the arrow, the vector that represents person 1, and I'm going to slide it across to the other side so that it points in the same direction, but it's on the other side of the box. Basically, all I did was take the arrow that represented person 1 and slid it to the other side of the box because that's how free body diagrams are usually drawn. So when I solve for the force that person 1 needs to be pushing in order to move the box, I'm going to need to solve for the sum of the forces in the x direction. So on the free body diagram, I'm going to have 270 newtons of force acting to the right. I'm going to have x newtons of force acting to the right also. And then acting to the left, I am going to have the force of friction, which is opposing the two guys trying to move the box to the right. So I'm going to draw the arrow, the vector, that represents the force due to friction. Again, friction is not a force, but there is going to be a force due to friction that we're going to have to solve. So when we solve for friction, the force of friction is going to be mu, the Greek letter mu, times the normal force. When I write mu, I'm going to write a mu with a subscript of a question mark because I don't know yet if I'm going to be dealing with static friction or kinetic friction. So the equation for the force due to friction is going to be mu times the normal force, which is N. The reason why I put a question mark as a subscript for mu is because I'm either going to be dealing with static friction or kinetic friction, and we'll figure that out later. So to find the force due to friction, one of the variables I have to solve for is N, which is the normal force. Since the box, the object, is not on a slope, the next question will be on a slope, but this question, the box is not on a slope, so the normal force of the box is going to be equal to the weight of the box. And the weight of the box is going to be the mass of the box times the acceleration due to gravity, because the weight of the box is a force, and forces go on free body diagrams. And a force is a mass times an acceleration. Since weight is a force and gravity is an acceleration, the weight of the box is going to be the mass of the box times the acceleration, which is gravity. So the mass of the box is written here in the question. It is 90 kilograms, and the acceleration of gravity is either going to be 9.81 meters per second squared if we're dealing with SI or metric units, and it's going to be 32.2 feet per second squared if we're dealing with American units or English units. So since this question is in metric or SI units and we're dealing with newtons, I'm going to use 9.81 meters per second squared because that's the units that we're dealing with. We're dealing with metric units or SI units. So 90 kilograms times 9.81 meters per second squared is going to come out to be 882.9 kilogram meters per second squared. And since 1 kilogram meter per second squared is equal to 1 Newton, 882.9 kilogram meters per second squared is going to be 882.9 newtons. So 882.9 newtons is going to be the normal force. Again, because the box is not on a slope, the weight of the object is going to be in equal and opposite direction as the normal force because it's not on a slope. So the weight of the object, which is measured in newtons, which is a type of force, is going to be the same as the normal force. They're just going to be equal in opposite directions. So I'm going to label the free body diagram N, which stands for normal force, equals 882.9 newtons. And if you remember, the reason why we found the normal force is so that we could solve for this equation right here, the friction force. So we know what N is, which is the normal force. Now we just have to find out what mu is. And the reason, again, why I put a question mark as a subscript for mu is because now we're going to figure out whether or not we need to deal with static friction or kinetic friction. If you want to know the difference between static and kinetic friction, you can click on link number 5 in the description, and it'll take you to my free body diagram explanation video, and we'll skip ahead to the part where I talk about static versus kinetic friction. So if you already watched that video, you basically know that the box is going to have to overcome static friction and then kinetic friction because the box is not already moving. It's asking how much force person 1 needs to push in order for the box to move. That means that the box isn't moving already, which means it's going to have to overcome static friction and then kinetic friction. So to find the values of static and kinetic friction, I'm going to pull up this chart that I have. This is not really an official chart. This is just the chart that I'm using. If you have a textbook or you want to just Google it, there's tons of these charts on Google. You can use a textbook. There's lots of ways to find coefficients of static and kinetic friction. So basically, you're going to go through this table and look at the two textured surfaces rubbing together. The question says that this is a 90 kilogram wooden box on a concrete floor. So the friction in question is basically what is the coefficient of wood rubbing against concrete. So I'm going to look on this chart and find wood on concrete. And I see that the mu subscript s, which is the coefficient of static friction, is 0.6, and mu sub k, which is the coefficient of kinetic friction, is 0.4. I know that the box is going to have to overcome both of them at some point, and since 0.6 is greater than 0.4, I know that the coefficient of static friction is going to come out with a higher answer than if I used the coefficient of kinetic friction. So this mu subscript question mark, I'm going to change to a mu subscript s, because I know that it's going to take more force for the box to break free and overcome static friction than it is for kinetic friction. So I'm going to plug in mu sub s, which equals 0.6 times the normal force, which will get the force of friction. So now to find the force of friction, I'm going to take mu subscript s, not a question mark anymore, mu subscript s times n, which is the normal force. So mu s is going to be 0.6, and the normal force is going to be 882.9, which is what we solved for earlier. So then the force of friction comes out to be 529.74 newtons, and it is acting in this direction. So then the last thing we need to do is figure out how much force does x need to be in order for the box to move to the right. So what we'll need to do is find the summation of the forces in the x direction, and I'm going to make it equal 0 so that we can solve for x. We can solve for how much force person 1 needs to be pushing. So the summation of the forces in the x direction, I'm going to say minus the friction force, which is F subscript friction. So minus F friction plus 270 newtons, which is the amount of force that person 2 is pulling, and then plus, because person 1 and 2 are working together, plus x, and then I'm going to make it equal 0 so that we can solve for x. So then I'm going to plug in the number for friction. I'm going to say the summation of the forces in the x direction equals negative or minus 529.74 newtons, and then plus 270 newtons plus x, which is the force that person 1 is doing. equals 0. So when I solve for x, x turns out to be 259.74 newtons in this direction. So in other words, person 1 is going to have to push 259.74 newtons in this direction in order for the box to move. Actually, technically, he's going to have to push harder because he wants to move the box. So I'm going to say that x has to be greater than 259.74 newtons in order for the box to move to the right, which is the answer to the question. What's the minimum amount of force that person 1 has to push in order for the box to move? Number 4, how much force does the person have to exert to push the 5-pound mass box up the concrete ramp? The box is 5 pounds of mass and is made out of wood. So the first thing I'm going to do before I actually draw the free body diagram is I'm just going to redraw this picture that I'm given here. I'll explain in a little bit. So first I'm going to draw the ramp. Then I'm going to draw where the ramp would be if this was a flat surface, which it's not. It's on an incline. And it's on an incline of 30 degrees. So I'll draw that here. Here's the box that's on the ramp. And then before I actually label it as a free body diagram, I'm going to go ahead and label this drawing that I'm going to do, and then I'll explain a little bit later. So the first thing I'm going to do is I'm going to draw the vector, the force of the man pushing the box up the ramp. So I'm going to label it F man. And then when the man pushes the box in one direction, the opposite direction is going to be the force of friction, which will oppose the man pushing the box up the ramp. Then I'm going to label the force of the weight of the box, which is due to gravity. And like I've said in my free body diagram explanation video, gravity, or weight of an object, will always act down, even if the box or the object is on an incline. So I'm going to label that with the letter W, which stands for weight. And then because the box is pushing down onto the surface with weight, the surface is then going to exert a normal force acting in the up direction, which I'm going to label as N. And then before I draw the actual free body diagram, I just want to make a note here that there is an angle between the actual gravity acting down and where gravity would be acting down if the box was on a flat surface. So what I want to point out here is that this surface is 30 degrees shy of being on a flat surface. So if this is 30 degrees shy of being flat, this is 30 degrees shy of being perpendicular to flat. So if this incline was resting flat on the surface, this would be 0 degrees. So if this box was resting flat on this surface, this would be 0 degrees. And if this was on the surface here, this would be 0 degrees. So this angle right here is the same 30 degrees as this angle right here. This is 30 degrees shy of being a flat surface. So this is 30 degrees shy of being perpendicular to a flat surface. So I'm going to label this 30 degrees. So like I said, that was not the actual free body diagram. All I really did was just recreate this picture right here. The reason why I did that is because I'm actually going to recreate the free body diagram. If you can recall, the whole point of doing free body diagrams is so that we can find the summation of the forces in the x direction and find the summation of the forces in the y direction. It's much easier when the directions are acting cardinal, which is up, down, left, right. So if we look at this picture right here, and we see what forces are acting up, down, left, and right, none of these forces are going in the up, down, left, right direction except for weight. This is acting straight down. But the force of the man, the force of friction, and the normal force are all acting in non-cardinal directions. So the reason why I recreated this picture to look like this is so that we can rotate the free body diagram 30 degrees, and then this force, that force, and this force will be in a cardinal direction. And then the only force that we have to worry about, the x and y components, is going to be the force of gravity, which causes weight. So now I'm going to draw the actual free body diagram. So I'm just going to draw a big old arrow. And then here is where I'm going to draw the actual free body diagram. The only thing I'm going to do, like I said, is I'm going to rotate it 30 degrees. Why 30 degrees? Because I want this force, and this force to be cardinal, and then I want this force to not be cardinal. 30 degrees because it's 30 degrees away from being on a flat surface. So now I'm going to recreate the free body diagram after tilting it 30 degrees. So here's the box. Here is the force of the man pushing the box, F subscript man. Here is the force opposing the guy pushing the box, which is force of friction. Here is the normal force. Notice how I said I wanted to get them all in cardinal directions. Well, now they are. And then, like I said, the only one that is not in a cardinal direction when I flip this and rotate it is going to be the weight. So because it's rotated 30 degrees, the weight on the free body diagram is going to be diagonal, tilted like this. And then I'm going to draw the x and y components. So here's the y component, and here's the x component. And since the angle between the actual vector and the component is 30 degrees, this angle right here is also going to be 30 degrees. So I'm going to label that like this. Okay, so now I have the actual free body diagram labeled. Now all I have to do is solve for the actual forces. And remember, when it comes to weight, because we rotated it 30 degrees, we're going to have an x component and a y component to solve for. So let's go ahead and do that right now. So the first thing I'm going to do when I solve for what they are is I'm actually going to start with the x component and the y component of this weight vector. So I'm going to label the free body diagrams. This is the y component, and this is the x component. So the x component is going to be mass, m, times gravity, g, times sine of 30, because it's 30 degrees, and we want the x component. If you need more help with this step, you can click on link number 3 in the description. So the x component is mass times gravity, sine of 30 degrees. So when I plug this in, the mass is 5 pounds, pounds of mass, times gravity, which is 32.2 feet per second squared, because we're dealing with American units or English units, and that is the acceleration due to gravity. That's g that we solved, or that we know. And then times sine of 30 degrees. Then the answer is going to be 80.5 pounds of force. Not mass, but pounds of force. So the x component is 80.5 pounds of force. That's this one right here, 80.5 pounds of force. So I'm going to label it equals 80.5 lbf, which is pounds of force. And then now I'm going to solve for the y component. So the y component is going to be mass times gravity times cosine of 30. Cosine of 30, because we're taking cosine of 30 because we want to solve for the y component. Again, if you want help with this step right here, you can click on link number 3 in the description. So the y component is mass times gravity times cosine of 30. So 5 lbm, pounds of mass, times gravity, again, 32.2 feet per second squared, because we're dealing with English units or US units, American units, and then times cosine of 30. And that turns out to be 139.43 pounds of force. That is 139.43 pounds of force in the y direction. So this guy right here, this y component is 139.43. So I'm going to label that here. 139.43 pounds of force. Okay, so now we go back to the free body diagram. We have the x component labeled, we have the y component labeled. Next, we're going to go to solving what friction is, the force due to friction, which is going in this direction. Because it's opposing, it's going against the grain of the guy pushing it in this direction. So next, I'm going to solve for the force of friction. So the force of friction, actually the force due to friction, because again, friction is not a force, but there is a force created by friction. So the force created by friction is going to be mu, the Greek letter mu, times the normal force, which is N. The Greek letter mu typically has a subscript right here that denotes whether it is static or kinetic friction. Because I don't know what it is right now, well, I do, but I'm gonna explain it in just a second. So rather than putting a subscript S or K, I'm going to put a subscript question mark, and then I'll go back to that later. So the force due to friction is the coefficient of friction times the normal force. The coefficient of friction could be static or kinetic friction. If it was static friction, the subscript would be an S. If it was kinetic friction, the subscript would be a K. So basically what we have to ask ourselves is what's happening in this scenario. The question is asking how many pounds of force does the person have to push to exert the 5-pound mass box up the concrete ramp. So the concrete box is not already moving. So there's actually friction that's occurring that the guy is pushing the box, and the friction is making his job harder. It's pushing the box this way. So static friction, if you look at my free body diagram explanation video, you can click on link number 5 in the description, and I will link the video, and I will jump ahead to the point where I actually talk about friction. So click on link number 5 if you want an explanation there. So basically what's happening is this box is not moving. It's asking how many pounds of force would it take to push the box up the concrete ramp. So the box is not already moving. So because of this, the type of friction that we're going to be using, the mu value, is going to be static friction because the box is not already moving. He has to jolt the box forward. It's not already moving. So he has to overcome static friction and then kinetic friction. And since static friction is typically higher because it's harder to move an object right from the get-go, he's going to be undergoing static friction. So I'm just going to rewrite that again. F sub friction equals mu and then subscript S, because I know what it is now, times the normal force. So I'm just going to go ahead and label what these variables mean. So I'm going to say where mu subscript s equals 0.6, which is the coefficient of static friction, S, static friction, which you can look up on a table or a chart. This is the chart that I'm using. It's a very, you can just find these on Google or in your textbook or whatever. So the chart that I'm using, I'm looking up wood on concrete because it's a wooden box. It's concrete ramp and a wood box, concrete ramp. So wood on concrete is going to be 0.6 for the coefficient of static friction. So mu sub s, where s stands for static, is going to be 0.6 for wood on concrete. And then N is going to be the normal force. What does that mean? Well, the normal force is the force that is equal and opposite to the force that is pushing down on the surface. So this is the force due to gravity, and this is the y component. The reason why we found out the the reason why we need the y component to figure out what the normal force is because the y component is equal and opposite to the normal force. So if 139.43 pounds of force is the y component, which is acting onto the floor, the normal force will then exert an equal and opposite 139.43 pounds of force back up onto the box for support. So we know that 139.43 is the y component. The normal force is the equal and opposite. So the normal force is going to be 139.43 pounds of force also. So we know what mu s is and we know what n is. Therefore, we can solve this equation. We just have to plug it in. So F subscript friction equals mu s, which is 0.6. By the way, these mu values are unitless. They do not have units. Like normal force, pounds of force, that's the unit. These coefficients are unitless. They do not have any units. So force of friction equals 0.6 times the normal force, which is 139.43 lbf, which is pounds of force. So then F friction, the force caused by friction, is going to be 83.66 lbf, which is pounds of force. So the force due to friction is going to be 83.66 pounds of force. So this force right here that's opposing the man pushing the box is going to be this, 83.66. So I'm going to, okay, fine, I'll label it. It's not going to look good, but equals 83.66 lbf. So the force of friction, which is this vector, this arrow, is 83.66 pounds of force. We know what the force of friction is. We know what the normal force is. I actually forgot to label it, but remember, we solved it. We talked about it here. We solved for the normal force, 139.43. So I'm going to go ahead and label that 139.43 139.43 lbf. So normal force 139.43, normal 139.43. So this is labeled, that's solved for. The y component is solved for. The only thing that we don't know is F man, which is the how much force this guy is pushing the box, but that's what the question's asking, so that's what we're solving for. We're solving for force of the man. So because that's what we're solving for, all we have to do now is find the summation of the forces in the x direction. Summation of the forces in the x direction. Because we want to solve for this, and this vector lives going side to side. It's in the x direction. So we solved for the normal force only so that we could help us find the force due to friction. We don't actually have to sum the forces because the normal force is going up and the y component here is going down. So we use this information to help us solve things, but when it comes to solving for F man, all we have to do is find the sum of the forces in the x direction because we want to solve for this force right here. The up and downs don't really make a difference. So that's why here we're just going to find the summation of the forces in the x direction. So the summation of the forces in the x direction is going to be the force of the man, which is what we're solving for, minus the friction force, minus because it's going against the grain, it's making his job harder, it's going in the opposite direction, and then minus this x direction of the weight, this arrow here, and then that's going to give us the summation of the forces, and then we just solve for F subscript man. So I'm going to write this out as an equation. I'm going to say the summation of the forces in the x direction equals F subscript man minus F subscript friction minus, I'll just do this, minus the x component of the weight, which is caused by gravity. So I'm just going to start plugging in the numbers here. So summation force x equals F man minus the friction force, which we determined to be 83.66 pounds of force, and then minus the x component of W, which is W is weight, which is caused by gravity. So the x component, this one, of weight is this one here, so 80.5 pounds of force. So 80.5 lbf. And then since we are trying to determine what force does this need to be in order for the box to move up the ramp, basically what we're saying is, what does this need to be in order for the rest of this equation to be anything greater than 0, right? Because if there's more force pushing the box up the ramp, the box is going to move up the ramp. So if we set this equal to 0, we can solve for the force of the man, plug in the numbers, and then find out what this number is. So I'm going to say 0 equals F man minus 83.66 minus 80.5, and then I'm going to solve for F man, which turns out to be 164.5 160.16 pounds of force. So to answer the original question, how much force does the person have to exert in order to push the box up the ramp? That's this, which rotated 30 degrees because of this, is F sub man. So this is 164.16. And then that is the answer. So thank you for watching. If you thought this was helpful, it would really help me out if you gave the video a like, because I am new to this, and it would really help me out if you gave the video a like so that I could share it with more people. So if you liked it, feel free to give it a like and leave a comment. And thanks for watching.